Okay, awesome. So the purpose of this meeting, it was requested that I meet and help you guys with the conjecture project. So we're going to work on the week 1 conjecture project, and we can work on whichever one you guys would prefer to start with. So if you guys want to look through that conjecture project, let me know which one would be helpful. And if needed, we can go through all of them, or you might kind of start to notice the pattern of how to prove a conjecture, and we may not need to go through all of them. But which one would be most helpful for you guys? All of them? Okay. Will, do you want to just go through the first one with me? So I'm going to kind of be coaching you guys through it. So I'm not just going to show you how to do it. I'm going to kind of coach you through how to think about it. Yes, Jody. So on this one, you'll have one conjecture for each of them. And the proof should be relatively short on these as well. Some of the other proofs will take a little bit longer, but you'll only have like one conjecture today. Yeah.
Okay.
Okay, cool. So, Will, do you want to just start on that first one and I can kind of coach you through that and then we can take turns and other people can take a turn for the other ones?
Yeah, that'd be great.
Okay, awesome. So I'm just going to share my iPad screen so we have some place to write. Um, okay. Okay, so what I'm seeing on the week 1 conjecture or week 1 part A conjecture is we're looking at the sum of 2 even numbers. So what is the conjecture that you want to state? The sum of 2 even numbers is always what?
Even.
Okay, awesome. Yep. So we would state that conjecture and we'd say, okay, the sum of 2 even numbers, oops, is always even. Okay. So Will, since I'm working with you on this one, how would you describe what an even number is, like conceptually? What is it that makes a number even?
Um, I don't know. The only thing I can think of is like 2 objects because there's 2.
Okay, sorry, my sound was a little bit quiet. Can you say that again?
The only thing I can think of is 2 because like there's 2 objects. 2 will always be even.
Okay, perfect. So 2 will always be even. What are some other examples of even numbers?
4, 6, 8, 10, 12 increments of 2.
Okay, perfect. So they come in increments of 2. Some of the things I'm seeing in the chat are things like pairs, or they make 2 even whole groups. So like one of the features of say like the even number 12 is you could put it into 2 groups equally with whole numbers. Versus like the number 11, you could technically put it in 2 groups, but you'd have to get into fractions and decimals, and they wouldn't come in whole numbers, right?
Yeah.
Um, Melissa, I love that analogy of socks. I'm seeing divided by 2 makes whole numbers. So there's kind of this overall theme when it comes to even numbers of needing to have pairs. And the number of pairs might vary. You know, like if you have the number 50, that means you have 25 pairs. But if you have the even number 28, that means you have 14 pairs, right?
Yeah.
So the way that we express that in algebraic notation is that an even number is a number that can be expressed as 2 times. I use the letter n in the instructions, but we can even think about it in words where it's 2 times an integer. So integers are like the whole numbers, but also the negative whole numbers like -1, -2, and so on. And this is like an algebraic way of explaining that idea of pairs. Because it's saying like whatever integer you're choosing, that's saying how many pairs you have. And an even number is one where you have two times some integer. Does that kind of make sense?
Okay.
So like, let's say, for example, the number 14 is even because we can express the number 14 as 2 times 7. 7 is telling us how many pairs we have. And because 14 can be expressed as 2 times 7, that makes it even.
Right.
So, with that information, we want to be able to prove why the sum of two even numbers is always even. So, to start our proof, what we would do is we're going to just define our two even numbers. So, we would say the first even number is going to be 2 times n, where n is an integer. And it might be 1, it might be 12, it might be 17. Like it doesn't matter what the integer is, but if it's an even number, by definition of what even numbers are, it will be able to be expressed as 2 times an integer. Does that part make sense?
Yeah.
And then if you want to add it to another even number, you're going to have another integer. So like this is just a sample example, but if we have 14 plus um, 6, let's say, this is an even number plus an even number. And if we were to put it into this notation of pairs, we would be thinking of it as 7 pairs plus 3 pairs.
Yeah.
And so the integers could be the same because you could also do like 14 plus 14. That's also a even number plus an even number. Um, but by definition of what an even number is, there are integers um, that you can multiply by 2 to get those two even numbers. Is this making
Okay.
sense? So,
A little bit. Yeah.
okay, cool. So our goal here is to be able to prove that the sum of two even numbers is an even number. So we want to be able to prove that this is equal to 2 times an integer. And it will be a different integer than the ones that like n and m. Because like if we look at our sample example here, 14 plus 6 is 20, which is 2 times 10. So this integer is different than these ones, but there is a relationship between them. What is that relationship? Like looking at this example. Hmm. Okay, yeah,
It's
so
still
Alexa,
even.
sometimes, oh, go ahead.
I just said it's still even.
Yep, so it is still even. Um, and like that's the thing we're trying to prove. And so we need to be able to show that like when you add these two things together, it equals 2 times some integer. And what would that integer be?
4.
Okay, so where are you getting the 4 from?
Well, you said 2n plus 2m, right?
Uh-huh.
So that would 2 and 2 is 4. Well, I guess with the variables might not.
Yep, so that would work if they were the same variable, like if you had 2n plus 2n, where they were both n's, you could combine them. But since they're different ones, um, we're going to use a different strategy. And we've got some people in the chat who have been commenting on it. So I'm going to look at their stuff real quick. So in the chat, Melissa said in like our specific example of 14 plus 6, if you look at the relationship between the integers of these two even numbers and the integer of the even number answer or like result of 14 plus 6, 7 plus 3 gives you the 10.
Mm, okay.
And then Jamie and Jody and Anita did this in the generalized case where they said 2n plus 2m has got to be equal to 2 times n plus m. So, like in this specific example, it was 7 plus 3 equals 10. And in the generalized case where you have 2 times some integer plus 2 times another integer, well, that's the same thing as 2 times the sum of the two integers.
Okay.
And basically that proves it. So in your conjecture proof, you'll kind of go through the reasoning that we just went through. So like you would say, we're trying to prove that the sum of two even numbers is always an even number. So let's have one of the even numbers be represented by 2n, because by definition, an even number can always be written as 2 times an integer. Then let's have the second even number be represented by 2m, because again, any even number can always be represented as 2 times an integer. So you're just kind of like talking through the reasoning of why these two expressions represent even numbers. Then you say, if I add these together, algebraically, I can rewrite it as 2 times n plus m. And this is like the reasoning you would use to describe this is the distributive property. Are you guys familiar with how the distributive property works?
Yeah.
So like usually we do the distributive property in this direction where we say like 2 times n, 2 times m equals 2n plus 2m. But you can also do it in the reverse process, which is called factoring, where you factor out the common factor and you do that common factor times the sum of the remaining factors. So in your proof, you'd say like, okay, I've got my two integers. When I add them together, I can rewrite that expression using the distributive property or factoring to factor out the two. And one of the properties of integers is when you add integers together, it creates integers. Like you can't add integers together and get a fraction. It's always going to be, well, I mean, technically whole numbers are fractions too, but like you're always going to get a whole number if you add two whole numbers together. And so that's why this proves that it's an even number always, because when you factor out that two, you have two times an integer. It's a new integer. It's the sum of the two previous ones, but it's still an integer. So that's how you prove that the sum of two even numbers is always even.
Okay.
Is that helpful? Does that reasoning kind of make sense?
A little bit. I gotta go. I am driving home on I-15 and I cannot focus on two things at once in this
Oh,
snow
yes,
blizzard.
please be safe. I will
So
post the recording in the conjecture assignment.
I will
Um,
watch that.
okay, awesome.
Thanks. Bye.
Yeah, I'm impressed you were as able to focus as much as you did. So thanks for being safe. Yes. Jody, yes, this one would be an equivalence. Yep. Really, the only time you're going to use a induction proof is one where the pattern builds on itself. So it's like, oh, you take the previous thing and you add something to it, or you take the previous thing and you multiply something. Those are the ones where you're going to use a proof by induction. Okay, so that was how we would prove part A, which was that the sum of two even numbers is even. Are there any of the other conjectures that you guys would specifically like help with?
Can I jump in right here? This is
Yeah.
Ken.
Hmm. Yep.
How do we use integers if an integer can be negative here?
Good question. So let's do a specific example where it might be negative. So this notation here works for any even numbers. But if we use a specific example, like maybe -4 plus, do you want them both to be negative, or do you want to have one of the integers be, or one of the even numbers be positive?
Doesn't matter to me.
Okay,
I'm
let's
just
do one with
wondering what
both.
will happen.
Yeah. So let's actually do -4. Oh, I chose 14 twice. Let's do maybe negative 20 plus positive 4. So we know that this equals 16, and this follows the rule of an even number plus an even number equaling an even number. Oh, sorry, that should be negative 16. So what that would look like in terms of the definition of even numbers is you would have two, like the two is representing the pairs, and you would have negative 10 of those pairs. And then for the 4, you would just have two pairs. And with the factoring thing, like if you do 2 times negative 10 plus 2 times 2, that's the same thing as 2 times negative 10 plus 2, which is 8, which is or sorry, negative 8, which is the negative 16 plus 2. So the proof is the same, regardless of whether the integer is positive or negative. Um, because like in this case, it was just that the integer was negative. But the structure of it is still 2 times an integer. Does that answer your question?
Yes.
Awesome. All right. So, which other ones would you guys like to do? We've got the sum of two odd numbers, the sum of an even number and an odd number, the product of two even numbers, the product of two odd numbers, and the product of an even number and an odd number.
Can I just ask one question first?
Yeah. Mm-hmm.
So I was watching your video, the one that you posted,
Mm-hmm.
and it made sense when you were explaining with like the pattern, but then when I was looking at the homework, I kind of got confused, like trying to compare the two and figure out what we were supposed to do.
Uh-huh. So it like any conjecture that you're proving, the structure of the algebraic expressions might be very different. So like in the one that I did in the video, I'm trying to remember what it was that I was proving it was equivalent. I think it was showing that n squared minus 1 was equivalent to like 2n minus 1 times 2n plus 1, right? That was what I
Something
was.
like that, yeah.
Yeah. So in that case, that was the conjecture. So if you guys actually look at the rubric for these assignments, one of the things that you get points for is stating the conjecture clearly. So in that case, what I was trying to prove was that the pattern of doing like odd number, like consecutive odd numbers multiplied together, that's equivalent to the pattern of squaring the integer and subtracting 1. That was my conjecture. Versus in this one, what we're looking at is that the sum of two even numbers is always even. And so the expressions that we're trying to prove are different. Because in this case, we have the two even numbers added together, and we're trying to show that that equals a single even number. So stating the conjecture clearly is the best place to start because it tells you what it is that you're trying to prove is equal. I don't know
So
if that
we
helps.
read, let me make sure I'm understanding. So we read the conjecture and then you write like the 2n plus the 2m, something similar to that, and then see if we can prove it.
In these ones where we're working with even and odd numbers, yes. Because the
Right, okay.
definition of an even number is 2 times an integer. Or we can do one with an odd number in just a minute, but the definition of an odd number is where you have some number of pairs, which is represented by 2n, but then you also have one extra one that isn't in a pair. So all odd numbers can be expressed as 2n plus 1. Or you can technically do 2n minus 1 too, like both of them work, but that's the definition of an odd number.
So could we do C then and talk about the even and odd together?
Yeah, totally. Okay, so do you mind being the one that I'm coaching?
Yeah,
Um,
that's fine.
okay, awesome. So C is the sum of an even and odd or product.
It's
I
the
think
sum
it's
of an even and odd number is.
okay, awesome. So our conjecture is the sum of even and odd is always what? So do you know what that is yet?
Well, we know what even number is, right, from the last one.
Mm-hmm.
So
But I mean,
that's the
like,
two.
Like, what's the conjecture? So like, if you add an even number plus an odd number, what type of number will it always be?
Always going to be odd.
Okay, perfect. Awesome. Now go ahead with what you were saying.
I was just thinking, like what we did on the last one, we had to do 2n plus 1, I think is what it'd be.
Mm-hmm. Yeah, so an even number, maybe I'll kind of color code these. So an even number, like we did on the last one, is going to be 2 times an integer. So I'm going to spell out the word, and then we'll use notation for it. But you have 2 times some integer. And then the definition of an odd number is that you have 2 times some integer, and it could be the same integer as the one that I've written in blue, or it could be a different one. And the 2 times the integer thing is just describing the pair idea, right? Because even numbers can be split up into pairs. Odd numbers, though, will have some number of pairs, but then you'll always have an extra one.
Either
You
a
know, like
plus or
number
a negative.
7. Oh, sorry, go ahead.
Either a +1 or a -1.
Exactly. Yeah. And I
Okay.
usually like to do plus ones, but you can totally do minus ones. Um, and I think you were the one that actually mentioned the sock idea, right?
Yeah.
So like the idea of an odd number is that you have some number of pairs of socks. That's this part. But then you have one sock that isn't in a pair. Does
Right.
that part all make sense?
Mhm. Yeah.
Okay, so that's the definition of an even and an odd. And we want to prove that this is equal to an odd number. So it's always an odd. So we want to show that this is going to be 2 times some integer plus 1, because that's the format of an odd number. And again, all of these integers are going to be different integers, or at least they could be different integers. Does that part make sense so far?
Yeah. Thank you.
Mhm. Okay, so now let's write it in algebraic notation without the words. So what letter would you like to use to represent the blue integer?
So let's do like X for that one.
Okay, awesome. So we're gonna have 2x. And then for the red integer, which one would you like to use for that?
Let's do K. So 2K plus 1.
Awesome. Okay, so this expression is the sum of an even and odd number, and it's any generic even and odd number. Like if it was, I don't know, 4 plus 7, let's say. What that's saying is you have 2 pairs plus, I think it'd be 3 pairs plus the 1 odd sock, right? But you could do this for any even and odd numbers. That's just a specific example. So now this is where the equivalence proof comes in, because we need to take this expression and make it so that it looks like 2 times some integer plus 1. Because we're claiming that this will always equal an odd number. And the format of odd numbers is that you have some number of pairs plus 1 extra.
Mm-hmm.
So how can we
So
get from here to something where we have 2 times an integer plus 1?
we'd have the 2 and then in parentheses would be X plus K, and then outside parentheses would be plus 1.
Perfect. Yeah, exactly. And to put this in context of this problem, 4 plus 7 is 11, which is the same thing as 5 pairs plus 1 extra. So like this 2 plus 3 gave us the 5, and that's where that X plus K is coming from. And that proves that the sum of an even and an odd is always odd, because you took a generic expression for an even number and a generic expression for an odd number, and you proved that that forms an odd number.
So when we're typing up this paper, we can kind of have like that expression in blue and kind of say, here's where I'm coming from, and then have the one in red and same sort of thing, and then just kind of have lines going down describing each thing.
Yeah, so on your proofs, you'll kind of write it like an essay. So you'll explain where each thing comes from. So like you'll explain where the 2x comes from, and you'll say any even number is a certain number of pairs And so let's have X represent the number of pairs. So 2X is the representation of the even number. And you'll just explain that in words, kind of like an essay. So you'll say our even number is going to be represented by the expression 2X because that's the definition of even numbers. And
Okay.
then our odd number will be represented by 2K plus 1 because again, any odd number can be written as a certain number of pairs plus one odd number that is not part of a pair. So like you're explaining where each part of your equation comes from. And then you would like say, I want to show that 2X plus 2K plus 1 equals 2 times an integer plus 1. Then you would say, because of the distributive property or factoring, I can factor out this common 2 that both of these terms have in common, and I can rewrite this part of the expression like this. And you'd like type that out in an essay form. So you'd say like, I can rewrite 2X plus 2K as 2 times X plus K because of the distributive property. And therefore 2X plus K or 2X plus 2K plus 1 equals 2 times X plus K plus 1. And because of the way that integers work, the sum of two integers is an integer. And so therefore this is an odd number.
Okay. And I remember the example you like wrote up too, or maybe I'll look back at that one too.
Say that again.
That made sense, yeah. And then you had that example you posted too. I'm gonna look back at that as well.
Okay. Yeah, and that just kind of gives you an idea of like how to intersperse like English explanations with the equations.
Mm-hmm.
So we kind of talked through the English side of it. So you're in your conjecture proofs, you'll just explain it. And it doesn't have to be super long. Like you might have one sentence that explains where the 2X comes from. Then you have one sentence that explains where the 2K plus 1 comes from. Then you have a sentence that explains why you can rewrite 2X plus 2K as 2 times X plus K because of the distributive property. And then you maybe have one sentence that explains why X plus K is an integer and therefore this is an odd number. Does that help?
Yeah, that sounds great. Thank you.
Cool. So we've done the sum of even numbers, we've done the sum of an even and odd. Would you guys like to maybe do the product of one of these? Okay, would anyone like to volunteer to be the one to be coached? So like the one that I'm having the conversation with?
I will. This is Anita. Can
Okay,
we do the product of two odd numbers?
yep, totally. It looks like you and Melissa were thinking on the same wavelength. You both asked for the same one. Okay, so our conjecture, let's state that clearly to start with.
So
Oh,
I'm trying to prove that the product of two odd numbers is always odd.
okay.
Is that what you want?
I gotta think about it for a second. So like if you do 7 times 3, 21, yeah. Yep, it's always odd. So product of two odd numbers is always odd. Okay.
So I
Um,
kind of just followed what you were doing with the addition, where
uh-huh.
so I just put 2n plus 1 is my first odd, and 2m plus 1 is my second odd.
Okay.
But I wanted to see what that looked like after we multiplied those through.
Okay, perfect. So you've got your two odd numbers. Great start on that. And we're just gonna multiply these together. So I'm gonna use like high school algebra notation since we're using variables and stuff. If you guys want to though, you can use X's or dots if that's easier for you guys to think about it, because I know you guys teach elementary school. So ultimately, we want to show that this is equivalent to 2 times some integer. We don't know what that form of the integer will take, but we want to have 2 times some integer plus 1 because we're saying that it is always odd, right?
Yeah.
Okay, so are you familiar? So people learn how to multiply expressions like this in different ways. One of the most common ones is foiling. Are you familiar with that?
Yeah.
Okay, so if
So
we
you
were to,
do the first ones, right?
uh-huh,
The first terms.
yep, so if I
So
multiply the first two, that gives me what?
4 and m as your
Okay,
first terms. And then
perfect.
you do the outers. So you've
Uh-huh,
got 1 times 1. Sorry, 2n times 1, and then 2m times 1.
uh-huh. Yeah, so the outers would be 2n times 1, which is 2n. And
And
then
then
the inners,
plus the 2m times 1 is 2m.
mm-hmm,
And then you're doing 1 times 1.
perfect. Yep. And for those of you who might not be familiar with foiling, whether you're on the recording or if you're listening right now, basically what this is it's double distributing. So you have these two terms right here, and you're distributing each one of them to the other set of parentheses. So like you do 2n times 2m, that was the f part of foiling where you multiply the first ones, and 2n plus 1 gives you the 2n, and then same thing with the 1. So if it's easier for you to think about it that way, like if you haven't heard of foiling before, that will give you the same result. Okay, so this multiplication of two odd numbers is the same thing as this, because foiling is just a way of finding an equivalent expression. So now what we want to do is we want to see if we can rewrite this in the form of being 2 times an integer plus 1. So we've kind of already got the plus 1 part, so that's great. And we just need to see if we can rewrite all of the other stuff as 2 times an integer. You have any ideas of how we might be able to do that?
So if you can you take a 2 out of the 4n and then a
Mhm.
2 out of each of the other terms, put that in front. So like 2nm plus n plus n. I mean, sorry, plus. So you'd have to have nm plus
Uh-huh.
n plus m. Is
Yep.
that what you're looking for?
Uh-huh.
Okay.
Yep. And
I
so
didn't know I
the
would take it that far.
yep,
Okay.
and the reason why you're doing it like that is just so that you can show that it's 2 times an integer. And as part of your proof, you would also need to explain why this is an integer. And that just comes from the properties of integers that says if you multiply integers together, you get integers. And if you add integers together, you get integers. That's just like one of the properties of that type of number. And so what that means is like this part right here where you have the 2nm, well, that's 2, which is an integer, times n, which is an integer, times m, which is an integer. So that whole number right there is an integer because if you multiply integers together, you get integers. And then if you take that integer and you add these other two integers, because integers plus integers always equal integers, that whole thing in the parentheses would be an integer.
And then the 1 on the end makes it an odd integer, right?
It makes the number as a whole an odd. Yep, because this is the result of multiplying these two odds. And because the format of it is 2 times some integer plus 1, that makes the result an odd, regardless of what n and m are.
Okay. That helps.
Awesome. The other two multiplying ones are kind of similar. In some ways, they're easier because like when you multiply even numbers together, so like let's say if you were doing an even and an odd, you might have 2n for your even number and then 2m plus 1 as your odd number. And if you multiply those together, you don't have to do the whole foiling thing. It's just single distributing. So it's in some ways easier because it's easier to multiply it. Melissa, you can if you want to. So if you want to say, like this whole thing is an integer, so therefore you have 2 times h plus 1, that's fine. You just need to explain why 2nm plus n plus m is actually an integer. So you don't have to say that. You can just explain it and say this stuff in parentheses, and like since you're typing it out, you would type out like 2nm plus n plus m is an integer because, and explain the whole reasoning of why when you multiply integers, you get integers, and when you add them, you get integers. And because that's an integer, you have the form 2 times an integer plus 1. And so if it's easier for you to replace all of this with a single variable, so it like looks simpler, you can do that. Just make sure you explain in your like paragraphs why that is actually an integer.
So it doesn't matter if we replace it or leave all that 2mn
Yes, you can do it either way.
stuff in there.
Yeah, the main point is that you need to explain that this is an integer, because that's the thing that makes it an odd number. And I hope this doesn't end up being more confusing, but the reason why it's so important to prove that it's an integer is because if you allowed any number, like any decimals and things like that, you could write an even number like 2, well, actually, let's do maybe 6. You could write an even number like 6 as 2 times a number plus 1, but that number would be a decimal. So it would be like 2 times 2.5 plus 1. So that's why it's so important that these are integers and that you're very specific that they have to be integers in order to make it be even, because otherwise it might like look like 6 is an odd number if you didn't make that specification that it had to be an integer. Hopefully that didn't confuse you more, but it's really important that they're integers. Because I guess with like the sock analogy, it's like saying that you have whole numbers of pairs of socks, not like fractions of pairs of socks. Yeah. So that's how you do the product of 2 odd numbers being odd. We also kind of briefly started an even number times an odd number. Are there any of the other conjectures that you guys would like to go over in more detail? All right. Well, in that case, sure. Yeah, Melissa, that's fine. Melissa, I know you already were the person who was being coached. Is there anyone who'd like to be volunteer to be the one to finish this one? Or maybe Melissa, you can do another one. You want?
Yeah, as
This
long as
is
you guys aren't
Jamie.
tired of listening to me.
This is Jamie. I can help with that.
Oh, okay, awesome. Let's do that, Jamie. Okay, so I'll rewrite our conjecture here. So for this conjecture, we're looking at the product because we're multiplying of even and odd. And based on multiplying even and odd numbers, what will the product always be?
Odd.
So ultimately, what we want to prove is that this is
Oh no, I'm
equal.
sorry. That's not necessarily true, right?
Let's each choose an even and odd number. So I'll choose 4 times 7.
Would
I
be
got
even.
20, so that would be even.
Yeah.
Okay, looks like Jody got the same thing, so we'll modify our conjecture, say that it's even. So that means that what we want to show is that when you multiply these together, you get 2 times some integer. And that integer is going to include the variables from the 2 original numbers. But ultimately, we want to show that you can write it as 2 times some integer.
Okay.
All right, so if we multiply these 2 expressions together, thankfully we don't have to do foiling because there's just a single term times 2 terms. which means we can just distribute once instead of having to distribute twice. And what would that look like when we distribute it?
4nm plus 2n.
All right. And if we want that to look like 2 times something that's an integer, how could we do that?
2 times nm plus n.
Like that? Oh,
Yes.
that could be an n. Okay, perfect. And why is this an integer?
Because we can multiply and add integers together and still end up with an integer answer.
Perfect. Yeah. And that's basically your proof. So like you'd explain where this comes from, explain where this comes from, explain that the distributed property gives you this when you multiply those together, explain that factoring gives you this, and then explain why this is an integer like you just did. And then that proves that that's an even number because even numbers are numbers that can be written as 2 times an integer.
Okay.
Nice. You guys are doing really great on this. This one like is one of the harder ones and you went through that really fast. So great job.
Well, thank you. You made it much easier.
Oh, I'm so glad. And also, I know Will left, but he was the one who requested this meeting, and obviously there were lots of people who wanted help with it. So thank you to Will for requesting this, and we'll continue doing this every Wednesday. So you're welcome to come when you want to, and if you think you can do the conjecture on your own for that week, you don't have to come. But if it's helpful, you can come every Wednesday, and we'll go through whatever the conjecture is for that week.
Is there normally
Where
going to
would
be
this-
like 5 or 6 conjectures, or is there like one some weeks?
Only if they're really easy ones like this. So like these ones are pretty fast, because it's just a matter of like defining the numbers, or multiplying them out or adding them together and then factoring them. So there's this one, I think next week you're proving exponent rules. I think there's 3 of them on that one. And then after that, I think it's just 1, because the ones after that take a little bit longer to prove. Yeah. Jody, the explanation is part of the proof. So, like I'll actually stop sharing my iPad screen and show you an example. Oh, I almost ended the meeting, sorry. Very glad I didn't do that. Okay, so if we look at my sample one, so what we've been doing have been equivalence proofs. So I'll look at the example equivalence proof. This is kind of the format of it. So the one that I proved was much more complicated than the evens and odds thing. But basically you state the conjecture, and for my conjecture, I had to kind of give an example of what that looked like. And then in your proof, I go through and I explain why I created this mathematical notation for my sister April's pattern in this example. And then, so like I'm kind of weaving the math into the paragraphs. And then I, like, actually, I don't know if I showed. Oh, so, I ended up showing that this is a restated version of my conjecture. So this is like in math language versus my original conjecture was that the pattern my sister found was the same as my pattern that I found. So I restate my conjecture, and then this is where I proved it. So notice that like I have like my expressions here, and then I explain when I multiply these expressions, this is what I get. So like in between each step of like calculations, I'm explaining how I get from each step. It makes sense.
Are you and your sisters all math teachers or something, or is your father just a sadist?
Hopefully we're not sadists. I'm a math teacher, she's not. My dad just really loves doing math, so he would always give us lots of patterns, and so it's kind of like a game for my family, like we play math. Um, which is probably why I became a math teacher, but she works at a bank.
Oh,
Um, so let's see in the chat. Suha, yeah, so all of the do you mean like working through an example, or are you asking for like a typed up version? Michael, this video will be posted in the conjecture assignment. So in the assignment with all the other videos and like the project guide, I'll post the recording there. So Suha, when you were saying you want some easier examples, do you mean like you want an example of what it looks like when it's all typed up? Okay. I don't have time to do that tonight, but I can type it up, and post that tomorrow. So you have an example of that. Yeah. Cool. Any other requests, before we end the meeting? Oh, good, Jody. I'm glad that it made it simpler. I'm not glad you were overthinking it, but I'm glad that this meeting helped simplify it for you. Okay, awesome. I will post this recording and also a simpler example in Canvas tomorrow, and I'll send out an email to let you guys know once that's posted. And I will see some of you guys on Wednesday. Jamie, yeah, you're always welcome to turn in stuff late. Like you don't get any late points taken off for it. But I just have it due on Friday because I like doing my grading over the weekend. So I'd prefer if you guys can do it on Friday usually, but if you need to turn it in late, you can still get full points for it. So I won't extend the due date, but you can turn it in on Sunday if you need to. My only caveat is it might take me a little bit longer to grade it, because if I do all my grading on Saturday and you turn it in on Sunday, obviously there'd be a little bit more of a lag there. Yes. Mm-hmm. Yep. Yep. All right. Okay. Well, I will see some of you guys on Wednesday, whoever decides to come next Wednesday. And I hope you guys have a good week. Thank you, everyone.